Hello, today I'm reporting a paper named 3D Human Pose Perception from Egocentric Stereo Videos. And this is the outline. First, abstract. With the growing compactness of head-mounted devices, significant self-occlusions in egocentric views have become a challenge, making it difficult for existing methods to precisely estimate complex 3D poses. In this work, this study proposed a transformer-based framework designed to improve the precision of egocentric stereo 3D human pose estimation. The framework includes two key innovations. The first one, it utilized deep features extract from a 3D scene reconstruction module based on uniformly sampled windows of stereo video frames. In the second one, it enhanced joint queries with temporal features from video inputs, enabling the model to better understand motion dynamics over time. This approach allows the framework to accurately estimate human poses even in challenging scenarios such as crouching or sitting. Additionally, two new benchmark datasets were introduced: Unreal Ego 2 and Unreal Ego Real World. These datasets provide a much larger variety of egocentric stereo views and human motions. Next, introduction and related work. Motion capture technology is transforming fields like motion analysis and XR applications. However, capturing accurate poses in unconstrained environments, especially with egocentric views, remains challenging due to self-occlusions in complex head-mounted devices, particularly during complex lower body movements like crouching. Monocular methods struggle with deep ambiguity and occlusions, while stereo methods, though capable of using deep, often neglect scene context and face complications like fish eye distortion in eyeglasses-based setups. And this study proposed a transformer-based framework for eyeglasses-based device. These methods leverage 3D scene reconstruction and temporal Curie augmentation to achieve more accurate pose estimation. Integrating first one is 2D joint heat maps for pose detection, and second one, scene depth from 3D scene reconstruction, and the third one, temporal context via joint Curie augmentation for capturing motion dynamics. This robust framework effectively handles challenging scenarios like crouching, leveraging temporal dynamics and 3D scene reconstruction to set a new standard for egocentric stereo 3D human pose estimation. And this is the mobile device for their data collection, featuring two RibCage RXO cameras, 12 centimeters apart with a 170-degree field of view. Its compact design captures high-quality data for diverse activities like walking, crawling, and dancing. Next is the method. And this is the framework. First, estimate the 2D joint heat maps from egocentric stereo fish eye videos in 2D module. The heat maps and input videos are then processed in segmentation module to obtain 2D human body masks. Next, using uniformly sampled windows of input frames and human body masks to reconstruct 3D scenes. Here, they render deep math and deep region mask from the reconstruct mesh. Finally, transformer-based 3D module process the joint heat maps, deep information, and joint queries to estimate 3D poses. Here, the 3D module leverages deep padding masks based on the availability of the deep math, as well as joint queries enhanced by the stereo video features from the 2D module. And next, I'm going to talk details of each steps. The first one is 2D pose estimation. These steps generates 2D joint heat maps for 15 key body joints, such as neck, arms, and legs, from stereo video inputs. These heat maps and intermediate feature maps are crucial for providing spatial and pose information that supports accurate 3D pose estimation in the next stage. Second, human body segmentation. This method reconstructs 3D scenes from egocentric videos by identifying background pixels using the EITH SAM model as the segmentation network. This approach extracts 2D joint location from heat maps and combines them with video frames to generate human body masks. Like this is the mask for both the left and right views. By guiding the SAM model with joint position, instead of relying on ground truth masks, they efficiently segment the human body, enabling accurate scene reconstruction without additional training. Next, 3D scene reconstruction. To reconstruct 3D environments, this study utilized uniformly sampled input frames and human body masks over 4-second windows. By applying structures from motion (SFM) through Metashape, they generate real-world scale 3D scene meshes and extract deep maps and deep region masks. This deep feature serves as essential cues for improving the accuracy of 3D pose estimation in the framework. This method ensures robust scene reconstruction, even in egocentric view, where self-occlusion and limited scene visibilities are common challenges. Furthermore, this approach tackles missing deep data by introducing techniques in 3D module to mitigate invalid values, making it reliable for complex real-world scenarios. This contributes to more precise pose estimation and expands the applicability of egocentric vision system. For this, because deep math can be missing in some frames, and to prevent processing features of such deep data and let the network focus only on valid frames, this study proposed to add padding masks V depth for all elements of depth features. 3D pose estimation method aims to accurately reconstruct human poses by integrating deep maps, deep region mask, and temporal context. These depth features provide spatial cues, while temporal dynamics are captured through joint queries, ensuring a comprehensive understanding of motion. Key to this approach is the transformer decoder, which efficiently processes these features and queries to estimate poses. Additionally, our stereo video dependent query augmentation enhances temporal features, enabling the framework to handle complex motions and maintain high accuracy across various scenarios. And this is the other training methodology, and it is centered on achieving accurate and consistent 3D pose estimation. The loss function includes the mean per joint position error, or so-called MPJPE, and negative cosine similarities, supervising both current and past frames to ensure temporal coherence. Key techniques include a deter-based transformer, decoder for efficient feature extraction, and adaptive Fourier augmentation, which enhance temporal consistency. Together, these approaches allow the model to robustly estimate poses even in challenging scenarios. And this page explains the design of the 3D pose loss function, which consists of two main components. And this one handles the pose loss as the current time step. And this one accumulates pose loss over the past t-1 steps, ensuring that the model leverages temporal sequence information. And the pose loss at each time step of this includes two parts. And this one represents the mean per joint position error, which measures the Euclidean distance between the predicted joint position and the ground truth, while this one represents the cosine similarity of the bone vectors, ensuring consistently the skeletal structure. Next is the experiment results. And this is the detail of the data sets they use. Unreal Eagle is an existing benchmark dataset with predefined splits and public baseline results, making it an ideal reference for evaluating new methods and ensuring comparability with previous research. And the expanded Unreal Eagle 2 dataset offers over 1 million stereo views and a greater variety of motions, significantly enhancing data diversity and improving model generalization. In contrast, while Unreal Eagle Real World focuses on real-world scenarios, its smaller data size makes it more suitable as a supplement for validating real-world applicability. By utilizing these three datasets together, it is possible to balance historical baseline comparison with performance evaluation across diverse scenarios. And the main evaluation way is mean per joint position error, which is used to measure the average error in 3D joint position predictions, indicating the accuracy of the model's prediction for each joint location. And the other one is the area under curve. This is the result of the synthetic dataset results for tables 1 and 2. Report the results with Unreal Eagle and Unreal Eagle 2. The results achieved over 15% better performance on Unreal Eagle and at least 40% improvements on Unreal Eagle 2, as measured by MPJPE. The qualitative results on Unreal Eagle 2 in the figure shows that its existing method and baseline fail to estimate lower bodies of complex poses with severe self-occlusions, such as crossing. And the left part is the MPJPE curve and visual output of the framework, while the right is the output of the method at frame 87 and 329 of the sequence, respectively. 3D pose estimation and ground truth are colored in red and green. And the result on Unreal Eagle Real World demonstrates that the method outperforms existing approaches, including the baselines by more than 10% in MPJPE as shown in table. Qualitative results in figure highlighted that prior methods often struggle with issues like floating feet, inaccurate pelvis positioning, and floor penetration, while the method accurately estimates 3D poses. The upper figure illustrates the model's consistently lower 3D errors and its robustness in handling challenging motions. Even when 2D heat maps closely estimate joint position, this approach excels at predicting accurate lower body pose, while the figure below is the visualization of outputs. This paper also conducted an ablation study, as shown in tables 4, 5, and 6, to improve understanding of how each component contributes to the framework's performance. Table 4 highlights the importance of deep padding mask, which filter invalid deep values and significantly enhance joint localization accuracy. Table 5 shows that these features reduce errors in lower body poses while maintaining upper body performance. Table 6 demonstrates that even with a single input frame, the transformer-based module outperforms existing methods, showcasing its robustness and the value of temporal context. These findings validate the design choice that underpin the framework's effectiveness. The conclusion. For the conclusion, this paper introduced a transformer-based framework that significantly improves the accuracy of egocentric stereo 3D human pose estimation. By utilizing scene information and temporal context through 3D scene reconstructions and Curie augmentation, the approach outperforms existing methods on challenging synthetic and real-world datasets. Thank you for listening.